Hi everyone, in this video I am going to show you that expected value of mean square error is equal to sigma square. Remember, we use mean square error to estimate sigma square, so we want to show that it is an unbiased estimator. So we are talking about ANOVA setting. So these are the experiments with single factor with let's say A levels. So let's start with the typical data for single factor experiment setting so that you can keep that in mind. So typical data for a single factor experiment. So basically this is how it's going to look like. You would record your treatment. So it's a single factor with A levels. So basically you have 1, 2, A treatments, A levels of the factor, or A treatments, or factor level in this case. And then for each factor level you have n observations. So we'll do it for same sample size, but this n could vary also. Ideally you don't want it to be different for different samples. So let's say we have our ith one here, so we would have yi1, yi2, somewhere here we have j, yij, yin, right? Now if it was different I would have called it n sub I, but I'm going to stick to the same one. It can be always generalized later. So when you do t-test, you have only two, 1 and 2, or A or B, two samples, and you are comparing them. So those two samples are coming from two populations, but here we have several groups, or two groups. Instead of two groups we have several groups, and we are going to compare several groups. So this is like our ith group or ith sample coming from ith population, and we are trying to compare A populations. So a statistical model for one-way layout is written as, let me just erase that so we have enough space. So we write the statistical model as yij equal to mu I. It's called Fx model, plus epsilon ij. I is going from 1 to A, j varies from 1 to n, and mu I is equal to mu plus tau I, where tau I is the ith treatment effect. And mu is the overall mean. So for each group that we are comparing, we can have their totals and we can have their averages. So this one would be yi dot, and this is yi dot bar. Yi dot is basically sum of yij, j goes from 1 to n, and this is sum yij divided by n. So this is the sum of the observations in this, and this is the mean of the observations in this group. Also, we assume that the error terms are independently and identically distributed with mean 0 and variance sigma square. So you will also, one more thing that you would see is y dot dot, which is the sum of all the observations that are here. Yij, I goes from 1 to A, j goes from 1 to n. So y bar dot dot is equal to y dot dot divided by A times n, which is the total sample size, and we can denote it by uppercase N. So the null hypothesis that we are testing is that mu1 is equal to mu2 is equal to mu A, and the alternate is at least one pair is different. Expected value of Yij is equal to mu plus tau I or mu I. So this is what does an effects model look like. We are breaking down the ith treatment mean mu I into two components, mu and tau I, right? That's what the effects model looks like. So also we assume that that sum of TIs is equal to 0. That is, the treatment or factor effects can be thought of as deviations from overall mean. Sorry, treatment or factor effects can be thought as deviations from the overall mean. So an equivalent way of writing this hypothesis, another way of writing this hypothesis is H0 tau 1 equal to tau 2 equal to tau A is equal to 0 against alternate that tau I is not equal to 0 for at least one I. So let's look at the expected value of mean square error. So mean square error is equal to expected value of sum of squares due to error divided by n minus a, which is 1 over n minus a, expected value of Yij minus Yi dot bar whole square. I is going from 1 to a, and j is going from 1 to n. So let's expand this. So we have 1 over n minus a, expected value of double sum Yij square minus 2 Yi dot bar Yij plus y bar dot dot square sorry this so I'm not going to write the subscript every time, what the first one is running over I and the second one is running over j. So if I look at this thing Yij, and this is Yi dot bar, and this is y bar dot dot square. So I can write this as, if I run the summation, so let me write it 1 over n minus a, expected value of double sum Yij square minus 2 times Yi dot bar, and then if I run this summation, so then it would be Yi dot, right, and then n for, because I is running, sorry, a times of that. So this is 2 times Yi dot bar multiplied by n Yi dot bar plus so this is I goes from 1 to a, So I'm just running the summation over j, and then this one would be y bar dot dot square, so which is y bar dot dot is double summation yij over a times n, and that would give me, if I run this summation, so I would get yi dot over a times n, and then yi dot over n would give me yi dot bar. So this is yi dot bar divided by a, and then I have an I which is running from 1 to a, and then there is another I and j here, so that makes it summation yi n times yi dot bar square. I goes from 1 to a. So this is just some side work. So expected value, use a different ink, it's too light. So expected value of mean square error is equal to 1 over n minus a. Expected value of double sum yij square minus n times yi dot bar square. Now we know yij is equal to mu plus tau y plus epsilon ij. That's the fx model, where epsilon ij is IID normal with mean 0 and variance sigma square. So this becomes 1 over n minus a expected value of double summation mu plus tau I plus epsilon ij whole square minus n sum yi dot square over n square. I just replace yi dot bar by yi dot over n, which is 1 over n minus a expected value of double summation mu plus tau I plus epsilon ij whole squared. Sorry, so it's a square bracket minus sum yi dot square over n square. Now let's look at all the terms that are here. So all the terms involving epsilon ij square and epsilon I dot square, the expectation of them are replaced by sigma square and n sigma square. Why? Because expected value of epsilon ij is 0, variance of epsilon ij is equal to sigma square. So expected value of epsilon ij square would be equal to sigma square plus 0 whole square, which is sigma square. Also, if you look at yi dot, it is sum of yij, j running from 1 to n. So it's j running from 1 to n mu plus tau I plus epsilon ij, which is n mu plus n tau I plus epsilon I dot, right? So 1 over n sum yi dot square is equal to 1 over n mu plus n tau I plus epsilon I dot square Now if you put all these things back there, and do a little bit of algebra, you would get, so replace, open this perfect square, run the expected sign. So what you're going to get is sigma square. Similarly, you can prove that expected value of mean square treatment is sigma square plus n sum tau I square over a minus 1. And that is why the test of hypothesis of no difference in treatment means can be performed by comparing mean square treatment to mean square error, right? If there is no difference, then sum tau I square would be 0, and those two mean squares would be equal. But if there is difference, the mean square treatment would be greater than mean square of due to error. And for that ratio, we statistically we can show come up with the distribution of that ratio, sampling distribution of that ratio. It turns out to be F. So I will leave it here. This is a bonus question. So just follow the steps here. Same steps, instead of a mean square error, you would write mean square treatment, and as long as you are able to replace the terms involving these quantities with what I have shown you here, you should be able to prove that expected value of mean square treatment is sigma square plus n sum tau I square over a minus 1. So I've already gone 16 minutes. I will stop here.